use ours and it'll be consistent everywhere. So the way you get to this is there's actually I don't have the method on here. If you open up UI responder, there's another responder method. I think it's, God, I forget the name of it. Do you guys know off the top of your head the name of the motion event method? Well, anyway, there's a method on UI responder, just like the touch events that we talked about last week for touches began, moved, ended, and canceled. There are also events for motion, and I can't remember them, but you can check it out in uiresponder.h. And the thing that you'll get through these events is a UI event that has type UI event type motion and subtype UI event subtype motion shake. Currently, that is the only subtype defined. So if you get one of these, you pretty much know it's that. But you should still check for it in case we introduce new ones in the future. And basically, this will get passed down to the first responder when the user shakes their device. So that's pretty cool. I mean, it's nice to know what direction the device is in. But what if you want to do something a little more interesting than that? If you really want to, figure out the user shaking in one direction, or you want something more raw. You don't just want what orientation the device is in. So you just want this. We just want this raw data, right? So in this case, we can find out, what acceleration is happening in different orientations. We want to get that directly and actually process it. So that's where we start to get into this accelerometer interface. It's also part of the UIKit framework. There's a UI accelerometer class. It delivers 3-axis data, so it'll give you X, Y, and Z for all the orientations that you might be interested in. It's got configurable update frequency, so you can sort of get updates either 10 times per second, 100 times per second, sort of tailored to what your app is trying to do. And it's delegate-based event delivery. It's pretty similar to the CL Location Manager class that we already talked about. So you basically end up getting the orientation something like this, right? You've got the Y that's going vertically through the device, X is going horizontally through the device, and then Z is coming out the front and out the back. So the accelerometer interface is the UI accelerometer class. There's a UI acceleration object, which will tell you, about the acceleration at a particular time. And again, a UI accelerometer delegate. So this probably looks pretty familiar. It's basically the same as the CL Location Manager interface. To configure it is slightly different. UI accelerometer, you don't allocate your own. There's a singleton one that you get using UI accelerometer shared accelerometer. You set the update interval so you can pick how frequently you need these updates, and then you set the delegate to yourself. This part's pretty important, actually. There's no begin and end generating updates like there is on CL Location Manager. Just setting the delegate causes the updates to begin. So if you want to disable to save power, the accelerometer, there's no method you call. You just set the delegate back to nil. It's a little odd, but yeah, that's how that works. So yeah, if you're not using the accelerometer data, but you've already set it up, set the delegate back to nil to turn off the accelerometer. Oops. All right, so yeah, event delivery begins as soon as you assign the delegate. All right, so defining your delegate object, right? You've got your accelerometer did accelerate method that you'll implement on the delegate. And that's going to give you back this UI acceleration every time that, whatever the frequency that you've asked for the updates are at. And from that, you can get the the acceleration's X, Y, and Z values, which are just floating point values that you can process to do whatever you want with the acceleration. There's only one delegate per application. There's a singleton instance. So if you've got 2 objects in your app that both need acceleration data, you kind of have to multiplex that yourself. So you have to set one object up as the delegate and then hand off the acceleration objects to the other 2 yourself if you need it in 2 places. And these things are delivered asynchronously on the main thread. So they're just queued up as events on the main thread. If your main thread is busy blocked, not receiving or processing events, you're not going to be getting acceleration events because you're blocking the main thread. They're delivered on the main thread, so another reason not to block the user interface. You also won't get acceleration events. So I kind of mentioned the range is sort of somewhere between 10 and 100 hertz. You can get, set it up anywhere in between those pretty much. The frequency really should be based on what you need. If you're just trying to detect rotation events, in this case you don't really need to worry about this because we've got all these other APIs for figuring out what orientation the device is in. But if that's the kind of thing you were doing, you don't need to update very frequently for that. 10 or 20 hertz is more than enough. The user's not flipping their phone around in a circle and trying to rotate the interface at that speed. If you're trying to control a game based on that and you really want direct feedback and something to happen right as the user moves the device, you probably want to up that to maybe 30 or 60 hertz to get more frequent input. But even 60 is getting pretty high. That's the frame rate of the device. So you may not even be rendering your game at that speed, depending on how complicated your OpenGL is. Yeah, as I mentioned, to disable the accelerometer events, you have to set the delegate back to nil, which it's a little odd, but keep that in mind as you start using this thing. If you're not needing the accelerometer data right now, set the delegate to nil. Your users will be happy because their device's battery life will last longer. If you want to start filtering some of this data, because we won't get into this too much, because this is more starting to tend towards frequency analysis, and it's kind of beyond the scope of this class. But there's two pretty basic things that we can kind of get at some really simple algorithms for real quickly, and that's a low-pass and a high-pass filter. So a low-pass filter would sort of isolate some constant acceleration. So if you're just holding the device still, but maybe just jiggling a little tiny bit, a low-pass filter would kind of get that jiggle out of there and just sort of show the basic general way that you're holding the device. A high-pass filter would be the thing that we do to allow that jiggle to be seen. You would see just the jiggle and not the stillness. So you use the low-pass filter to sort of get more large-scale changes and smooth out the acceleration data, and the high-pass filter will give you more user-intended movements, like smaller movements, basically. So if we start taking a look at some of this and plotting it on a graph, right? So let's say we're holding the device straight up and down. We're going to see no acceleration in the x or z directions because we're not moving in those directions, and we're holding it straight up and down. So y is going up and down through the device. In this case, you can see in the middle of that graph there, there's a steep drop where it went down. That actually is where we turned on monitoring of acceleration, right? Because we're holding it this way. Since we're on Earth, we got 1g of acceleration because that's what we got. So you can see that right there on the graph. It's actually at -1 because it's pointing downwards. So let's kind of pull that out there. That's our -1g of acceleration. So if we wanted to take that and actually figure out the frequency of it, you'd sort of start wanting to use a Fourier transform. We won't talk about that too much right now. You can kind of, it's more advanced signal processing than what we're going to be talking about here. But the basics of what you'd be doing would be basically converting from the time domain to the frequency domain, right? So the graph on the left is the time domain. We're seeing over time what the acceleration values are. If we convert to the frequency domain, it's basically showing us the frequencies that we're seeing in that graph. So in this case, we're seeing a constant frequency at 1g, right? But if we start to shake, so let's kind of take our device and start doing that, then we're going to start seeing something different on our time domain. The acceleration is going to start going up and down. But in this case, you can see here, it's actually still centered around the -1g because we still have that acceleration from holding the device vertically. So so now our frequency domain actually shows both of those motions in addition to the standard gravity. So let's say we wanted to isolate just the orientation that we're holding it in, right? So that we just want to isolate that constant force of gravity. In this case, we're going to try and apply a low-pass filter, which will get rid of that, the horizontal movement that we introduced. So we really just want that thing in the middle, the one frequency that was showing where we were originally holding it. So the way we'll do that is with a low-pass filter, which will pass just that low frequency values. There's certainly more complicated ways you could do this kind of thing. This is a super simple example. In this case, our low-pass filter is basically just going to weight the previous value at 9/10 of the new value. So as the value is changing over time, it's going to tend towards whatever the previous value was. So if you're if your acceleration in this case is 1, just holding it still, and we're just moving it up and down, we're fluctuating between like -0.5 and -1.5 as we move up and down. But we're always sort of centered around that 1. So if we keep preferring the previous value, we're always going to sort of tend to stay around 1.